Hi guys, welcome back to the channel. Today we'll be looking at exec system call, which enables us to execute new programs. We have already looked at fork, which enables us to run an exact replica of the running process. The replica created has the same program in it. Exec is the way where we can replace this program with an entirely new program. Let's look at the system call arguments and the return values. Execve is the name of the system call. It returns an integer variable. It is taking path name as the first variable. It is taking a list of character pointers which could point to strings, and it is also taking an environment list which is also a list of character pointers. We'll look at how we can populate argv and envp in an example program. Execve never returns on success. The very fact that it returned is an error. -1 is the error value, and we can check the global error variable to see what was the exact error. Process ID of the new program remains the same. This is because the existing process now runs a new program. The old virtual memory address space is replaced with a new virtual address memory space which maps to the new program. The text section, heap section, stack section, data segments are built from scratch for the new program, and it replaces the old program in the running process. The effective user ID of the process, which dictates the access level it has on the system, remains the same as that of the original process. This doesn't apply for SetUid programs, where the effective user ID is now changed to the real user ID of the program we are executing. So for example, there is a test program file with a UID of 100 and group ID of 200. If we pass this test as a path name variable to execve, then the effective user ID would be changed to the user ID 100, and effective group ID would be changed to group ID 200. The set user ID bit of a file could be checked with ls-l, where it would depict s instead of x in the execute permission. So if this test file is read and write with set user ID, it would depict S here instead of the execute. Some of the errors in case of execve could be e-access, where the access permissions of the path name file is not available. It could be ent, which means that the path name program that we are passing does not exist. Exec would mean there is no execute permission on the program that we are passing. E to big means the arguments that we have passed to execve are beyond the allowed maximum limit. Let's assert our understanding with the help of an example program. I'm going to write a program where I'll be invoking execve with one of the arguments that I pass as a command line argument to this program. I'll be populating the arg vector, the environment vector in this program, and passing it as an argument to the execve call, where the first argument would be the command line argument that I pass while invoking this program. One of the things to keep in mind is that the command line argument would be stored in argv1 and not argv0. argv0 is always the name of the running program. So the first command line argument would be stored in argv1. Let me write another program, print args, that I'll pass as the command line argument. Here I'll be iterating through the argv vector and printing the contents. I'll be doing something similar for the environment variable as well. As you can see, exec has returned and it has printed an error saying bad address, which is fine because we didn't pass any command line argument to understood exec program. Let's look at the program output after fixing all the errors. The printed args program has been exec and is able to read through the argv vector and the environment vector and is printing them onto the console. Let's look at the family of exec calls. Exec VE is the actual system call, and all these functions are the library implementation on top of exec VE. All these functions would internally invoke exec VE itself. It's just that they differ in the arguments that are being passed to them. To be able to understand them, let's keep these four things in mind. L represents the list, V represents a vector or an array, P represents the path name variable, and E is the environment list. If you find L inside the function name, then the second argument is the list of strings with the last string being null terminated. If you find E in the exec function name, then it would also be passing the environment list as a vector. P inside the exec function name represents that it will be searching the path name variable for the file name that you provide as the first argument. So if P is not there in the function name, then you have to provide the full absolute path name. If P is present in the function name, then just the file name is sufficient because this file name would be searched for all the directories in the shell path variable. So exec LE would be passing the environment list as a vector, a list of null terminated arguments, and the path name because the path variable has not been provided. Exec LP provides the path name searching, so file name is sufficient. With exec VP, just file name would work because by virtue of P, this file name would be searched in the path name variable. We have to provide the arguments inside a vector. Exec VE also provides the argument inside the vector, and path name is needed because the file would not be searched in the path name variable. Exec LE, we can give arguments as list of strings with null terminated string at the end, and the first argument as the absolute path name because path name variable searching is not available. I would also like to emphasize that if the environment list is not passed as an argument, then caller's environment list is inherited in the new program. If we want to override and don't let the new program have access to the parent's environment list, we can provide an explicit environment list with the help of exec LE or exec VE system call. It is also important to understand that file descriptors are preserved across a exec system call. This is an important point to note because this is how shell executes most of its redirection operations. Let me explain this with the help of this shell command. This shell command would write the output of ls command into dir.txt. But how does that happen? We know this is the redirection operation, but fundamentally, what shell does to make the output of ls go into dir.txt? The first step that happens when we execute this command is that our current shell would fork a child shell. Child shell will then open a file descriptor to dir.txt with fd1, which is the standard output. There are multiple ways to do that. Whenever a program is run, the standard output is always opened with fd1 and standard in, which is the keyboard, is always opened with fd0. These two file descriptors are available to program as soon as they start. The child shell would first close the file descriptor 1 and then open a new file descriptor to dir.txt. Kernel would always assign the lowest numbered file descriptor for the open system call. Now, since the file descriptor 1 has been closed, the subsequent open system call for dir.txt would assign fd1 for dir.txt. The child shell would then exec a ls system call. A ls system call by default writes its output to standard out, that is fd1. Now when this ls tries to write the output, the fd1 has been redirected to dir.txt in the caller child shell, due to which whatever ls writes goes into dir.txt. If we don't want the new program to inherit the redirected file descriptors from the caller, we would set a close on exec flag on the file descriptor. This will automatically close all the file descriptors once exec is performed. If exec fails, the file descriptors are still available in the caller. They'll only be closed on a successful exec. Implementation of pipes also happens by redirecting file descriptors. We'll talk about pipes in inter-process communication and understand how the redirection happens there. It is also important to note that all the signal handlers are lost once a exec is performed. This is because the entire memory of the process is replaced.